again, as it's changing, so the waves are different in different parts of the world.
What about tides? Because tides.
That will be the moon and the sun, you know.
Yeah, but like around the UK, you have like the currents as well. And
Yeah, they are currents, but they are not that high compared to these loads. Wave is a massive load, right? It gives a big load. Now, wave, for the design purpose, we need two parameters: the wave height and the wave frequency. That means, during the wave height, you have different load acting on your foundation. Because they have more the wave height, more the load, right? And wave frequency is how many times per minute it is hitting. So we would need two parameters: wave height and wave frequency. Typically not see this 10-second period. So every 10 seconds you get a maximum at 10 seconds. But in other parts of the world, they are different, right? So wave will act somewhere, say here, the resultant wave. So if I put the resultant wave, it's acting there. Right, so that's the wind load, that's the wave load. What else loads are there? Self-weight is there, of course. I mean, let's say you have the environmental load, other load. Another load is this 1P load. What is 1P load means? As I told you about the, think about this big 40 tons blade. There are 3 blades, yeah? So 3 blades, you really can't align them properly. Because there will be always misalignment, because you are having a big jack of birch, you take this big blade, you attach it there, so you really can't align them properly, like a mass imbalance, a little bit of mass imbalance. Plus, when you put the blade has got a shape. The blade pitching, so the blade has got a shape, a shape. That shape may not be perfect. So that causes a misalignment. It's similar to your washing machine, you put it on a floor. Why vibrates? It shouldn't, if you do it properly. Because there will always imperfection. So this 1P load is basically, as the blade turns, it gives a small vibration. And that is to do with the amount of imperfection. So bigger the structure, bigger the imperfection. Because there is more error in manufacturing, more error in putting things together. Right? That's the 1P load. 1P is basically a particular wind turbine can operate in a range. Say, turbine can operate in a range from say 5 to 14 RPM. So a typical turbine, if you see the wind is not very high, very slow wind, is going at 5 RPM. So 5 times per minute. It's very slowly moving. Wind is very good, blowing nicely. You can see it is going at 14. Sometimes 6, 7, 8, 9, 10. Then sort of 14. So that's the range. So if you see any turbine, they will tell you what's the range at which it can operate. Right? And this term is called cut-in speed. Cut-in speed, and that is called rated RPM. Rated RPM. Rated means if you turn at 14 RPM, you get the maximum power that is rated for. And cut-in is the minimum speed. You will not see it operating at a lower than 5. Right? What really happens is that there are so many moving parts. So moving parts will give you alternating stresses, and that can cause a fatigue damage. Right? If the wind is blowing very low wind, they don't operate it. Because what happens, you produce power, but you do more damage to your system. So more damage to the fatigue damage you do. Right? Because why this life comes around 30 years? They're all coming from the fatigue life. And if you have this steel structure in the ground, there will be alternating stresses, and that cause the that cause a fatigue damage. So your fatigue life is finished at the end of 30 years, right? So what happens if the wind is very low, it will operate at say 5 RPM, not lower than that. Now, 1P load. What is the 1P load? Suppose it is turning at 5 RPM, 5 times a minute. So your 1P is the frequency of that 5 RPM, and that is the basically at what it would oscillate. So 5 RPM, if I convert to hertz, it will be 5 by 60. And that is the frequency of the oscillation of that tower. The magnitude depends on the how much imperfect that whole thing is. Okay? That is the 1P load. So 1P is basically the load due to misalignment of the rotor nacelle assembly. So at the top, this is known as rotor nacelle assembly. So RNA. Right? So they're all given in the notes. This chapter. So you can basically read everything. They are there. So don't worry if you miss out some words, but they will explain somewhere here. Okay. They will be somewhere here. Okay. Now, what is the 3P frequency? Any idea what that 3P stands for? So 1P means the range at which it can produce power. So 5 to 14 RPM, right? And what's that 3P stands for? Now, this is a tall tower, yeah? 110 meter tall tower. So the wind will blow as well. So now think of the load on the tower. The load on the tower would be, when the blades are not in front, you get the full load on the tower. But when the blade comes in front, what do you see? Shadowing. Right? So what you will see, the tower will experience a big load and a small load. Big load, small load. As soon as the blade passes the tower, there is a drop in the load. And that would be 3 times the RPM. Because if it is moving at 5 RPM, that shadowing will be 5 times 3, then there are 3 blades. Right? So that's 3P is for the blade shadowing effect. How does the blade shadow the tower? So you see a drop in the tower load, again back up, right? Yes? Now, another interesting thing is, this structure has got a frequency of 0.22 Hertz for 8 megawatt turbine. For 8 megawatt, I will show it in a more detail, 0.22 Hertz for 8 megawatt. For 3 megawatt, 0.34 Hertz. Typical wave can be quite close. So what happens if a structure frequency is quite similar to the frequency of the load? What happens? Resonate, right? Exactly. So that's why these things can resonate. Okay. So that's what can happen. Now here is a. Now why they're different? Here is the offshore oil and gas structure, and here is the offshore wind structure. Look at the differences. The difference is, first of all, offshore oil and gas jacket, you get a large vertical load. Now this top side can weigh 10,000 tons, 12,000 tons, 12,000 tons. This top side, entire thing. And that being taken by, this jacket will have 4 piles, four legs. Each leg may have 3 to 4 piles. So 16 piles are supporting this big jacket. So here the vertical load is very high compared to lateral load. Lateral load is not very much because they are not high structure. Right? The lateral load is very less. So these piles are mainly loaded vertically, big vertical load, and less lateral load. They are very long, 60 meter, 80 meter long, 60 meter, 80 meter. These are very long piles, very small diameter. They are like 2.1 meter, 48 inch, 60 inch, 84 inch. These piles are very long. On the other hand, here, look at this structure. So you have got a lot of large moment. Because the top, at hub level, you can get 2 millimeter of load, lateral load. So look at the very large movement. And compare that less vertical load. Right? And they are large diameter. So effectively, these piles are moment resistant. So you design a pile to have the moment resistant. So these piles resist moment. On the other hand, these piles are there to carry vertical load and smaller lateral load. Right? So you cannot really borrow the principles from here and use it there. You need a lot of thinking. What happened over the years, industry started, because there are many guys who knows to do this pile design. They simply use the same sort of principle to carry out this design, and there are some sort of setback, but they are trying to recover. So there's a lot of things going on, research how to sort out that. Okay, another big problem, big difference is the frequency of this structure is around 0.3 hertz, and this is more than 0.6 hertz. So the wave frequency is 0.1 hertz in North Sea, so you are far away from resonance, but here you are a bit close. So this gives another big difference, that they are sensitive to dynamics. So dynamics is a very important thing to consider in this design, and here it is not. Right? So here are the main sort of differences in these two type of structures. Now, so what is the problem here? The problem is, you have got a new technology, you have got a big turbine, you have to design them for 30, 40 years, you don't have track record, how will it work? So you are basically very cautious, and you have to do a lot of research. So that's the main thing. So what we have to do, to learn from other disciplines, is a similar problem elsewhere. Could we solve that particular problem? Can we get the knowledge from there and use it here? So if you look at whole engineering practice, it always evolved from failures, learned, upgraded, changed, made it bit more perfect. So this particular industry is going to that phase. It's learning. It's learning and improving. If you improve and learn, the cost comes down. Right? So this is where we currently stand. However, you know what is O&M? You know what is O&M?
Operation
And maintenance. So why is there what happens? Suppose you put a big wind farm in London area somewhere, and it is producing power happily for many villages, houses. Suddenly you see the blade is cracking. The blade starts to crack. One blade is large blades, right? One blade starts to crack. What happens? No, it will work, but you would. So what happens is the blade starts to crack. You will start to have a big imbalance, because look, the blade has to be symmetric to cause it to, perfectly aligned. If the blade starts to crack, then you start to see more vibrating. If it vibrates, it can set resonance. Then it can have failure. If it fails, you have to change. So what's the option? you have monitored them. The blade has to crack, fine. But you change a blade, it's easy to change a blade. You need to hire a vessel, the crane, get the right people, get the certifier, get the insurer, and you start finding out whose fault, who will pay the liability, and who's liable. Is it a fault in the design? No, it's not my problem. You have to push it on. So it's quite a bit of a thing, right? It's a new industry developing. Yeah. So this is where we are also working in this area, right? Now let's take a break. Actually, is it? Take a break. You want it? Yeah. Why don't you take a break? 10 minutes, 15 minutes, 15 minutes.